The previous lecture talked about the classification of thermoplastics based on usage. So applications in terms of their mechanical properties, their price per pound, how many billions or millions of pounds are sold annually or used annually. Now we're going to get into the classification of thermoplastics based on their family, and what I mean by family is chemical family. So these are the ones we're going to be talking about, and we're going to be starting with the polyolefins. In other words, we're going to be going from commodity, quasi-commodity, engineering to specialty, but we're going to be talking about those at this point forward based on their chemistry. So the first one is polyolefins, and that refers to polyethylene, polypropylene, and their copolymers. This particular lecture, so lecture 6, A and B, are going to be talking about mainly polyethylene. Then we'll talk about polypropylene in lecture 7. When it comes to polyolefins, each one of these families has a little bit of a history lesson to go along with it. The reason I like to do that is this. There are other disciplines that are very old. Chemistry is one of them. That goes back to medieval times. When it comes to plastics, we're really talking about the last 150 years. Now that 150 years is a long time compared to the lifespan of a human being, but when it comes to the lifespan of an industry, it's very short. So I like to talk about these things in context with when it comes to the advances are happening typically, at least within my lifetime, and you will see changes in the plastics industry within your lifetime as well. So the first big breakthroughs in the plastics industry were the invention of stereospecific catalysts. That was done by this gentleman, Carl Ziegler, and I believe his name is Giorgio Natta. He's Italian. And these allowed for the production of linear polyethylene. And this, in other words, came about to make high-density polyethylene that we use extensively today. And that was, the Ziegler-Natta catalysts were the ones that were used extensively until the early 90s. And then Exxon, Dow, and Chevron Phillips came up with metallocene catalysts. And this has really good activating efficiency, methyl aluminooxane and bis-cyclopentadienyl metal compounds. Don't worry, you're not going to have to say that or be tested on it, but that's what they are. And then when they started using these catalysts, these metallocene catalysts in the early 90s, they had enhanced clarity, toughness, strength, and barrier properties for polyolefins. Not only polyethylene, high-density polyethylene, but also polypropylene as well. When it comes to polypropylene, it has a wide variety of unique properties. Again, you're going to see this kind of format repeated throughout the chemical families. I'll talk about their unique problems, the challenges that they have, some applications, maybe some other specific things that have to do with additives or things like that in regard to a specific chemical family, but they're going to kind of follow the same format, and then we'll wrap it all up with applications. So, good news, if you see the application slides coming up, it means that you're in the home stretch and the lecture is almost over, and you can move on to important things like nap time or food. So, when it comes to polyethylenes, it has a variety of unique properties. This has a very low TG, and this is negative 120 to negative 115 Celsius. This is lower than most commercial rubbers. Now, TG. To put this in some context, the lower the TG is, the more molecular mobility it has at low temperature, the more flexible it is at low temperature, and that is an advantageous property. Now, the reason polyethylene is not like a rubber at room temperature is because polyethylene is highly crystalline. This is a semi-crystalline polymer, and it can have up to 95% crystallinity in high-density polyethylene. So low-density polyethylene has less because it's branched. High-density polyethylene can have up to 95%. So the reason that polyethylene is not rubber-like at room temperature is because of its high crystallinity. I've now said that twice. This might lead you to believe that it might be tested. Polyethylene, however, is limited by a number of things. It does have low tensile strength compared to other polymers. For example, PET can get up to 40,000 psi, whereas even high-density polyethylene only goes up to 5,500. Polyethylene needs significant modification to withstand outdoor conditions. It doesn't do well to UV light exposure and heat. If you put a little bit of carbon black in there, it can reduce this problem, but not completely avoid it. Polyethylene is very susceptible to environmental stress cracking. It has relatively high gas permeability, so this increases the susceptibility to environmental stress cracking. If you increase the molecular weight in the polyethylene, that can reduce the problem somewhat. You can also reinforce it with butyl rubber, either through a blend or through a copolymerization with a little bit of butadiene. but it's still very susceptible. It's one reason why zip ties, which are primarily polyethylene, don't do so well for multiple seasons. Polyethylene is highly flexible, and it's highly flexible without the use of plasticizers. And plasticizers are an additional chemical. We'll talk about them a little more when we talk about polyvinyl chloride. But they're an additional small molecule. They can present some environmental or health problems, and so being flexible without the need for plasticizers is advantageous. It's also easy to process. Polyethylene melts at relatively low temperature, and you get a flexible bottle that can be used for squeeze bottles or films. When it comes to all blown films, 60% of the polyethylene used goes into blown films. What are blown films? Things like trash bags, shopping bags, anything like that, and sheet material. Polyethylene has good resistance to acid, alkali, and salts. The only exception to this is a strong oxidizing agent. This is highly used in household detergent bottles. Most of these are polyethylene. Polyethylene also has low moisture absorptivity. Very, very low for LDPE and MDPE, medium density polyethylene, almost none for high density polyethylene or ultra high molecular weight polyethylene over a 24-hour period. That also makes it easy to process because you don't need a pre-processing step of drying. So you can take stuff out of the Gaylord, throw it into the hopper, and you don't have to dry it first. That is a concern with other materials, so this also reduces the amount of time spent on preparation. Polyethylene is a very good material for electrical insulating, so you'll see wire coating with polyethylene routinely. We'll talk about other things that have good electrical insulating properties, but if you can get away with the environmental conditions that polyethylene can withstand, typically you're seeing polyethylene insulation for electrical cables. I know you were thinking, Gene, this is supposed to have some chemistry in it. When are we going to see some chemistry? Don't worry, we're going to start to see some chemistry. So, this is the reaction to make polyethylene. You have ethylene monomer, shown here. You polymerize it to make polyethylene. Ta-da! How you polymerize and what catalyst you use kind of determines the outcome, but it's as simple as that. So, ethylene polymerized to make polyethylene. Once again, if I'm asking you, if I give you this structure, and you tell me it's ethylene, I will cry multiple tears, I will put a sad face on your paper. You don't have paper, this is all virtual, but still, and remind you that if you see brackets and a subscript here, that it's a polymer. So, brackets, subscript, poly, something or other. Now, this subscript here is the degree of polymerization, so however many number of these repeat units is present, that's what that means. Now, depending on how you polymerize and what you use, depends on the product that you get in terms of its form. So here are some properties of polyethylene. Low density polyethylene, medium density polyethylene, linear low density polyethylene, high density polyethylene, and ultra high molecular weight polyethylene. So low density polyethylene has the lowest density. That would kind of be based on its name. And then as you go up, you get greater density. Linear low density polyethylene is similar to low density polyethylene, but it is not branched in the chains. It is linear. And then high density polyethylene has the highest density, highest level of crystallinity. So once again, as you go from low to medium to high, you see an increase in crystallinity. As you go from low to medium to high, you see an increase in the melting point. So in other words, more energy that has to go in to melt it to process it. You tend to get an increase in mechanical properties as you increase the crystallinity as well. And you tend to get fairly consistent elongation properties across the board. Ultra-high molecular weight and linear low density I'll talk a little bit more about. Applications of polyethylene is a function of density and melt index. So medium density polyethylene is often used in film, pipe, blow molding, and rotomolding. Linear low density, again, film, pipe, and blow molding. Linear low density, film, blow molding, tubing, extrusion coating. There's linear low density for the purpose of injection molding. A lot of HDPE goes into injection molding. And then high molecular weight HDPE for film, pipe, and blow molding. So one thing to keep in mind is this is the density, and then this is the melt index. As the melt index goes up, the molecular weight goes down. And of course, as the density goes up, the crystallinity also goes up. This is a representative structure of low density polyethylene. The reason why the crystallinity is lower is because there are these branch points off of the chains. It's these branch points that keep the density of the polyethylene lower. It prevents a lot of the crystallization. So this structure right here can stack really, really easily on top of something that looks like that. But if you put a branch point there, it prevents that stacking, and that's what reduces the amount of crystallinity in low-density polyethylene. Now, when I'm talking about crystallinity among the polyethylenes, I'll say that this has low crystallinity. But when I'm talking about crystallinity between polyethylene and, say, nylon, even low-density polyethylene still has higher crystallinity than a lot of nylons. So polyethylenes across the board are very crystalline of the semi-crystalline polymers. This is HDPE. Now this is a nice regular structure, stacks on itself really well, and this is a nice flexible molecule, so it can kind of bend back on itself and stack up and make lamella and all kinds of crystallites, and forever and ever. And so that's why this is high density. High density in this case is due to the high level of crystallinity. High density polyethylene resembles decane, this particular small molecule in structure, which also crystallizes very well. When it comes to catalysis and reactivity, low-density polyethylene is made by free radical polymerization. The same way you would make, say, a methacrylate, polymerization, things like that. This is also called high-pressure polyethylene. Ethylene itself is a gas, and so under high pressure you can get it to liquefy. So then you can get better reactivity. Low-density polyethylene is highly branched, and it has low crystallinity compared to high-density polyethylene. Again, it's still 40 to 60%. The major application for low-density polyethylene is films. Here is a high-pressure method reactor for your information. High-density polyethylene is made by Ziegler-Natta catalysis, or some of the metallocene catalysis, and this is a group 1A to 3A transition metal plus a group 4B to 8B transition metal. And these are some examples. So you have a titanium chloride with an aluminum ethylene chloride. One of the ways they refer to these when you're using these particular catalysts these are the TICL catalysts, so TICL, TICL, haha. So this is TICL 3 and this is TICL 4. So that's one of the ways these are referred to. This is done at atmospheric pressure, and this produces a highly linear, highly crystalline product, so 70 to 90% crystallinity. So if you ever hear low pressure polyethylene, this is the low pressure or high density polyethylene. Ziegler-Natta and solid state catalysts do have some problems, and that's why the metallocenes were invented. Some of the stereo control is not great, and that's not as important for polyethylenes, but it is for polypropylene. And these catalysts also produce contamination. So the metallocenes were developed, and these were soluble single-site catalysts. They produced a lot more stereo control, especially for polypropylene. It's easier to get the catalyst out, so you don't have a laborious second post-processing step after the synthesis. You got nice homogeneous molecules, better control of stereoregularity, and very narrow molecular weight distribution, highly uniform product. Much more advantageous for injection molding. So this is a diagram of the Phillips process. Once again, this is not something you're really going to be quizzed on, but this just kind of shows the setup and the type of reaction conditions. So 0.06 chromia on aluminum, 150 to 170 Celsius. This is, believe it or not, this is a relatively low temperature and relatively low pressure to produce high density material. And this is the Ziegler-Natta procedure, so lower pressure and temperature and similar product density. Now, there were some applications in which a linear product was advantageous, but not one that crystallized as extensively as high-density polyethylene. So linear low-density polyethylene was developed. So this has a similar density to regular low-density polyethylene, but it is linear. The chains themselves are long, they don't have branch points. So what it actually is a copolymer of ethylene and 6 to 9% of some other alpha olefin. And these alpha olefins include 1-butene, 1-hexene, or 1-octene. And this is Ziegler-Natta catalyst again. This is a gas phase fluidized bed reaction. If you've never seen a fluidized bed, I have a video in the polypropylene lecture. This is also done at atmospheric pressure, and it has crystallinity similar to polyethylene, but it has better tensile properties than low-density polyethylene. And that's why this was developed. Once again, this is the modified gas phase fluidized bed type reactor setup. So for your information, Another type of polyethylene is ultra-high molecular weight polyethylene. This is defined as polyethylene with a molecular weight above 3 million grams per mole. So if it is below 3 million, it is not ultra-high molecular weight. If it is above 3 million, it is ultra-high molecular weight. This is for coatings, sheet, tape, or wear strips. So something that needs to have high abrasion resistance and a low coefficient of friction. So that's why this was developed. And ultra-high molecular weight has superior impact resistance even in cryogenic or very low temperature environments. This has really good lubricity. In other words, it's slippery and it has a low coefficient of friction. It doesn't cake or stick. It has good sound dampening properties, and it has good chemical and stress cracking resistance. When it comes to polyethylenes, most of them have terrible environmental stress cracking resistance, so this is an improvement on that. Also, this is easy to machine. And when it comes to the electrical insulating capacity, it is one of the advantageous properties for polyethylene. It has a very, very low dissipation factor. So what is dissipation factor? Dissipation factor is the amount of electrical energy converted to waste, in other words, heat, by a material. So a good electrical insulator has a low dissipation factor. And polyethylene is very suitable for low voltage electrical insulating. So your average kind of household type insulating. And it has good dielectric strength as well. And it varies somewhat based on low to high or ultramolecular weight, but has very good insulating properties for a commodity, low-cost polymer. So once again, we see our little stop sign, and this is where I'm going to stop this video. We'll pick up other properties and applications of polyethylene in the second Lecture 6 video.